So if you are considered in the part of conducting material, it's have that two different types: the high resistivity conducting material, then high conductivity conducting material, again the superconducting material, and the normal conducting material like copper and aluminum, which is we are using in the major conducting part of the machines, right? Then the insulation material we discussed based on the various operating temperature, right? The various operation temperature, it's starting from 95 to up to 180 degrees Celsius and above we discussed. Based on the operating temperature, which are the types of insulation we require, so we can select most appropriate one, that is the insulating material. Then the magnetic material in the category, it is majorly classified three types, that is the dia, para and ferromagnetic material, right? So in that ferromagnetic materials have comparatively high permeability, that is why we are selecting for the ferromagnetic material, which is most appropriate for the machine design, right? That is the part of electrical engineering material. The last class we discussed about the continuation of that is the phase factor. The phase factor, that was the definition you all know. It's denoted as SF. It should be equal the conductor area to the ratio of conductor area to the total winding area. The conductor area in the conductor area, it means it is the which are the conductors we are using in the machine, that is the conductor area to the total winding where we are wound in the winding in the electrical machine, the stator or either rotor, that is the total winding area or total winding occupied area. Okay, that is the phase factor that we have discussed. Then continuation of that, the main dimension, diameter and length of the machine we discussed. The diameter, you all know, if you are considered the electrical machines, so the front view, so that what is the diameter, this one is the length, right? If you are considering any type of machines, so there will be a length and the diameter, that was the main dimension that we are going to design it. So before that, you should know the total electrical loading and total magnetic loading. Total electrical loading, it is the flow of current multiplied with the total number of total number of conductor. So that is the ampere conductor per meter. Then similarly, that is the total electric loading, and total magnetic loading in the sense there will be a number of poles multiplied with the induced flux. That is the total magnetic loading. Okay. From that specific electric and magnetic loading we discussed. The specific electric loading, that is denoted as ampere conductor. No, so that is the AC. It should be equal the total electrical loading IZ into Z divided by pi into D. That formula we are used. So that unit is ampere conductor per meter square. Right. That is the total specific electric loading. Similarly, the choice of specific magnetic loading, that is the BAV, that is the flux density, average magnetic flux density. Sometimes they may call it as average magnetic flux density. So it is also the total magnetic loading, that is the P pi divided by pi dl. Right? So in that we consider another one notations, Weber per meter square. So that is the tau, that is the pole pitch, that is the pi d by p, right? So the pole pitch also we consider while we are solving the problem. This also used. So these are all the things we have discussed in the last class. So the continuation of that, we are trying to solve one problem. So the problem, what are the data they are given? What is they are given? What is the power rating? The P should be equal to 400 kilowatts. Then how much volt they given? Yeah, 500 volt. The V should be equal to 500. Then 450 RPM. Yeah, RPM in the sense you have to notate it capital N. Then 6 volt. The P should be equal, number of volts P should be equal to 6. Then what? Yeah, armature diameter D should be equal 0.87 meter. Similarly, the length 0.32 meter. Then the lab winding, they are used for the lab winding, LAP. Lab wounded DC motor, right? Lab wounded DC motor. Why they are considered the lab winding in the sense? The lab winding, the armature parallel path, it should be equal to number of volts. You should remember these things also because it is used in the problem. Okay. So then lab wounded. So they are asking you to find any data is missing here. Huh? Yeah, total number of conductor they are given 600. 660, 660 total number of conductors, is that it should be equal to 660. So they are given this. From that they are asking you to find the average magnetic flux density or specific magnetic loading or specific electric loading. So that is the given data. You should write like that. The given data, then that to find AC and BAV. So what are the formulas you are used? Again you can write like that. Formula used. So the AC it should be equal to what is that? IZ, Z divided by pi into D. Similarly, the BAV it should be equal to P pi divided by DL. So after writing this formula, you should analyze what all the data is available here. Then what all the data you need to find it out. So in that particularly while you are calculating the ampere conductor, that is the choice of specific electric loading. In that current you should find. Current they are not given, right? So the current you should find. Similarly here diameter they are given, pi is the constant, Z value that is the total number of conductor they are given. Then the average magnetic flux density it should be equal to number of poles they are given. Pi you need to find it out. So what is the formula available to find the pi and IZ? That you have to identify again. Okay. If in the given data itself, if they are given the I value and pi value directly in the straight away you can substitute in the formula, then you can find it out easily. Okay. So but they are not given. So you need to find it out the flux. So you know all. It's a DC motor. You know the back EMF equation. That is the EB. It should be equal P pi N Z divided by 60 A. So you see here the A and as well as A value is missing. Remaining all values you all know, but the A value is missing here. That is why they are given the law binding the P equal to A, right? So you can substitute. So from this formula, from this equation, you can find it out easily. The pi value. The pi it should be equal to what it will come? EB into 60 into A divided by here. It is this value where it will come. It is multiplied with the numerator. This will become denominator. The P into N into Z. So you can substitute this value, right? So you all know the back EMF, that is nothing but here they are given the voltage. It is the EB. You can assume it, right? So you can substitute this all value. So the EB value is 500 into 60 into 6 divided by 6 into 450 into 660. So both 6 from, because here itself you can write like this, A equal to P. So from here itself we can, because of lag binding, here itself we can eliminate it. So the remaining value we can find it out. That is the pi value. What is the value is coming? You can check it and tell me how much it is coming. 0.001 Weber. Okay, now you are finded, don't discuss. Now you are obtained the pi value. So the obtained pi value you can substitute here. So that is the BAV. It should be equal. You see here, P is the number of poles 6 into what value you obtained? 0.01101 divided by pi. That is the constant. You can directly use it. Here the diameter they are given 0.87 into 0.32. See here they are given the meter itself they are given. So you don't need to multiply anything. So if you are obtained this value, that is the Weber per meter square. Okay. So you can obtain and find the value. What is the value is coming here? 0.693 Weber per meter square, right? That is the BAV. Similarly, you need to find it out. I is at first. then you can substitute IZ value and remaining all values in the equation, then you can find the ampere conductor, right? So how you can find the IZ value? We have another one relationship. Don't discuss. IZ, we all know what is the formula for power. P, it should be equal P into I. So here in any motor you can find it out, right? You can find it out the flow of current, that should be the armature current, right? That is the armature current. So from that you can find it out the armature current. Here the power value they are given P divided by V. So what is the value is coming? That was the armature current, right? Here they are using in the lab winding. While we are finding the IZ, that is the actual flow of current. IZ, it should be equal armature current divided by number of poles, right? That is the formula, right? So first you have to find it out this value. What is the value here? 0.60, but here the power they are given in terms of kilowatts, right? So the power 400 kilowatts. The power value is 400 kilowatts. So you have to 400 into 10 power 3 divided by the 500. What is the value of armature current? That is the 800 ampere. So here the 800 divided by number of poles, how much? Number of poles 6. So what is the value of IZ? 133.33 it is continuing, so you can 34 ampere, that is the IZ. So now you are obtained the IZ value, right? So you are obtained the IZ value, then you can substitute the AC, it should be equal IZ into Z divided by pi. What is the formula? IZ into Z divided by pi D. So you can substitute all the values. The IZ value is 133.34 into 660 conductor divided by pi into what is the diameter? 0.87. So you can substitute and find the value. How much it is coming? How much it is coming? Yeah, 30. Yeah, 32,196. Okay, 198. Yeah, the 0.2. Yeah, 0.2 you can approximately you can negligible value because the conductor it's not in the 0.2, right? So 32,198 ampere conductor per meter square. That is the total number of conductors. Total loading. That is the specific electrical loading, right? Be all clear? So first you have to write it out given data based on your given problem. You can write the given data, and the given data itself you can analyze what are the data they are given. So there is no data ideal, right? What are the data they are given, that all you should use it. Likewise, usually they will give the data like that. Okay, that is why the power and voltage, you can see the problem. After solving this problem, you may see the power we are used, voltage and speed and number of poles, diameter, length, and the even their weighting also we are considered, right? The lab winding, then the total number of conductor. So that what all the data you should use it, right? So after that, after writing up given data, what you should find, that you have to write it separately. Then what are the formula you are going to use it, that you have to write it. Then you can identify it. So here what are the data is missing from the given data, that is how you can find it out, that you have to analyze yourself based on the previous expressions, right? So the IZ, so while you are finding the electrical loading, flow of current, you should find from the given data, right? So that is there you are using this formula, P it should be equal to V into IA. Similarly, you are finding the armature current. So after finding of armature current, you can find the flow of current, that is the formula, IZ by P. Sorry, IA by P. So from that you have found the total flow of current. From that you are founded electric loading, specific electric loading, that is the AC, right? Is it clear? So likewise you can write the second problem, try to solve it yourself.